During our energy unit, we talked about this concept of power. And power is just defined as how much energy we use over a certain amount of time. It essentially represents the rate at which something is using or transforming energy. And so we saw the formula that P is equal to any change in energy divided by an amount of time that goes by. And energy was just in joules, time was in seconds, and so our unit for power, which was watts, was in really joules per second. That's what a watt really is. So it's a rate at which energy is being used up or transformed. But we've also now learned a different kind of formula that represents how much energy gets used by an electrical load. And we saw in our previous lessons that the energy used by an electrical load can be found by taking the voltage, multiplying by the current, and also multiplying by how long we use that load for. So let's try and put all of this together. So in general, power is equal to the energy we're transforming divided by time. But energy, we just saw, was voltage multiplied by current multiplied by the time that we're using the thing for. And then if we want power out of that, we still divide by how much time went by. But what you can see is that we have time now on the top and the bottom, and those will just cancel each other out. And we arrive at just a very simple statement: voltage multiplied by current. That actually is what's equal to power if we're just dealing with electrical loads inside of circuits. So we'll actually pull that all together and just call it equation 1. So power, even though it's technically energy divided by time, in electric circuits we can think of it as voltage multiplied by the current. And we'll just call that equation 1. Because as we'll see, there are two very similar versions of that equation that we can also produce that relate to power. Of course, we have to keep in mind that we may be presented with situations where we either maybe don't know the current or we don't know the voltage. And we want to try and use Ohm's law to come up with situations that can still allow us to find the power. So if we start with the law we just described, that power is equal to voltage multiplied by current. Well, remember, Ohm's law tells us a few things. So it tells us that voltage is equal to I times R. So I can replace the V in this first equation here, P equals VI. I can replace it with I times R, and then I still multiply by current. So really, this is just me replacing voltage with something that's equal to voltage, I times R. But what you'll see there is that we're multiplying the current together in two spots. So a simpler way we could write this is that it's really the current value squared, or multiplied by itself, times the resistance. And so another way we could write the power equation is power is equal to our current squared multiplied by our resistance. If we happen to know current and resistance but not voltage, we can use what's now called equation 2 to help us find it. But we can also do a little bit of rearrangement with Ohm's law, because Ohm's law also tells us that current is equal to voltage divided by our resistance. So I can replace current in this other equation with V over R. So I'll keep the voltage from the original equation, but I'll replace the I with V over R. And again, the idea is that I've just taken this current of I and just replaced it with something that equals the same thing. But now again, you can see that voltage is multiplying by voltage again. And so we get V squared, and then if we divide that by resistance, we'll get the power. And so this leads us to a third version of the equation. So we can say that P is also equal to voltage squared divided by resistance. And of course, that would then be useful for situations when we don't have the current, but we do know the voltage and the resistance. And we'll call that equation 3. So we keep all of those in mind and just use them in different kinds of situations. Having a better understanding of electrical power then gives us an easier way that we can try and figure out how much electrical energy will be used and how much that might cost us. So, for example, most appliances tend to have some kind of power rating on them, which gives you a rating of how quickly they're using the energy. And then we just track how much time we're using it for. And what we saw even back in our energy unit is that we can find the amount of energy by taking the power and multiplying by the time. In appliances, most of the power that you'll see is actually rated in kilowatts, how many kilowatts of power that thing uses or can transform. And we just measure how much time in hours we use that for, and then we can figure out the energy consumption in what they call kilowatt hours. And we talked about this unit a little bit back in our energy unit, because it uses kilowatts in it, but remember the overall unit is actually an energy unit because we're multiplying by a time. We're multiplying by the number of hours. And I've just shown this little calculation for you once again, but we already actually saw all of this stuff presented in our energy unit, but it's just a little reminder that 1 kilowatt hour can be easily converted to joules by just taking 1 kilowatt, or 1,000 joules per second, and multiplying by 1 hour's worth of seconds, which is 3,600 seconds. So we get that 1 kilowatt hour is actually about 3.6 million joules, or about 3.6 megajoules is the other way that we could say that. But once again, if we can figure out how many kilowatt hours an appliance is rated for, figure out how many hours we run it for, and if we know how much electricity costs for each kilowatt hour we use, we can easily use those factors to figure out how much the electrical energy is going to cost us. So let's take a second and do a little example of that. So if we want to know how much it's going to cost to run a 1,000 watt toaster for 2.5 minutes, if power costs about 12 cents per kilowatt hour. Well, let's write down some things that we know. We're told the power in watts, so that's 1,000 watts. But again, we eventually want to be able to get our energy amount in kilowatt hours. So it's useful if we actually convert this right away into kilowatts. So we could call this exactly 1.0 kilowatts. That's what 1,000 watts really means. Time then, we're given as 2.5 or 2.5 minutes. If we can get that into hours, then we can easily use these to find kilowatt hours. So I'm going to take that 2.5 minutes and realize that if I divide that by 60, or think of it as a fraction out of 60, the decimal answer that I get will represent how many hours we have used. So it's about 0.04167. That's how many hours we are technically using the toaster for. And I know that seems weird when we have an amount that's just a small number of minutes, and we try and convert that to hours, but it just means we'll have a very small decimal number of hours. But we can still calculate it in hours, and now it's in much better shape for us to easily calculate the energy. And that's what we're going to have to do first. We're going to have to do a little quick step where we figure out how much energy in kilowatt hours we're actually using. So the energy, remember, is just your power multiplied by the time that you're using that powerful appliance for. So it's going to be 1 kilowatt multiplied by 0.04167 hours. And so when we do that, pretty simple math, it's just 0.04167 kilowatt hours. It's nice when you're just multiplying things by 1. Makes the math pretty easy. So in step 2, we want to actually find the cost. So the cost, if I just sort of write this out as more of a word statement, it's going to be the number of kilowatt hours, which is another way of saying the energy, and that's not a hashtag symbol, that's number of kilowatts. And then we just multiply that by the cost per kilowatt hour. So more mathematically now, that's 0.04167 kilowatt hours multiplied by 0.12 or 12 cents per kilowatt hour. When I multiply something in kilowatt hours by something that has kilowatt hours on the bottom of its unit, because that's per kilowatt hours, those just cancel out. And when I multiply those together, I actually just get about, in dollars, 0.005, or about 0.5 cents. So really just about half a cent is what it's costing you to run that appliance. We'll talk about this in a little bit more detail in class, and I welcome you to ask questions at that point.